everybody. Welcome back. Hope you were able to find some refreshment during our short break. I'd like to welcome Pontus Brandt to the virtual podium. Pontus is our project scientist for the Interstellar Probe Study, and he's going to be sharing with you the results of a few years now worth of gathering what the science goals are and how we're going to go about achieving them. Pontus. And also we're welcoming Elena Provornikova, who's going to be providing some of the content here as well. With that, Pontus, the floor is yours.
Hey, thank you very much, Michael. I don't know about you guys, but this pandemic has really put a strain on everybody. I think Zoom fatigue is a real thing. But you know, really, this science here, I think, is what inspires a lot of us to keep going. Okay, so over these past 4 years, we have been on sort of a journey where we've all formulated this compelling, groundbreaking science enabled by an interstellar probe. And this is now, as both Ralph and Michael said, has culminated in the mission consult report, of which many of you been a core part of it. So thank you. And once this report is out, I really encourage you to read it because it really is important for us as we're going into the decadal survey as well. Okay, so here Elena and we will take you through the summary of the science goals, the questions, the objectives, and tomorrow you will hear more about their implementation in terms of measurements and also instrumentation. There's a lot of info here to distill and digest, but I think you can now download this full presentation from the website, and you can follow along, and maybe that will encourage you to also ask more detailed questions. So, but before we go through all of this, I want to make a shout out to what has made all of this possible, and that is, of course, all of you. I've showed this in the past workshops, and it still holds true. It's all of you. It's this growing team and momentum out in the community that's really made all of this possible. So, and really what's behind of all this is, of course, the drive to explore that really counts and will continue to count as we head into the Solar and Space Physics Decadal Survey. So what we will present today is the result of this large community organized across 8 working groups right now. We started out with about 65 participants back in the Explorers Club in 2018. That grew to about 86. And then last year, I think we had 250 registered participants in the latest virtual workshop, and today I think we're at about 200 registered participants. And on the membership list that we have online, I think we're pushing up to about 500 members across the globe. So all of you had guided us to why we want to fly an interstellar probe. So that's really sort of been the team journey here. But so let me now take you on a slightly different kind of journey. So as you know, our sun is just one of 100 billion stars in the galaxy. And during its evolution, the sun with its protective magnetic bubble has completed nearly 20 revolutions around the galactic core. And during this evolution, or during this journey, it's plowed through widely different environments. It's witnessed supernova explosions on its past that have all shaped the system that we live in today. And these vast differences in interstellar densities, speeds, charge fractions have been responsible for an extreme range of sizes and shapes of the global heliosphere throughout this history, from many times bigger than what it is today to a tiny heliosphere that even got below the orbit of Earth, perhaps. And this in turn has had dramatic consequences for the sort of penetration of the primordial soup of interstellar material that have made all of us, and that have affected several crucial aspects of elemental isotopic abundances, atmospheric evolution, and perhaps even conditions for habitability. And as far as we know, only some 60,000 years ago, the sun entered what we call the local interstellar cloud, and is now at the very edge of it. And it turns out that in a mere couple of thousand years, we may find ourselves being completely outside this the local cloud, and likely entering into a very different environment. So yet again, the sun and its protective bubble on its journey through the galaxy is about to undergo a transition that will shape its continued evolution and also fate. So Interstellar Probe would go, of course, farther and faster than any spacecraft before, through the boundaries of the protective heliosphere into the unknown interstellar cloud, far beyond where the Voyager mission will ever reach, to understand these processes that shape our bubble, our heliosphere, our home in the galaxy. And the way we've come to think about this is that Interstellar Probe represents a snapshot of our place along this solar journey through the galaxy to determine the current state of the heliosphere and its surrounding interstellar space, to ultimately understand where our home came from and then where we're going. As Ralph already said, the mission concept study is driven by 3 goals. The primary goal is focused on understanding our habitable astrosphere and its home in the galaxy. Here, a dedicated in situ and imaging payload would explore the new regime of space physics in this boundary and beyond in the interstellar medium. And this science has driven then the design of the baseline mission, as we call it, under heliophysics. NASA has also asked us to assess the science value to other disciplines, and it's clear that an outward trajectory like this holds really big opportunities for exploration of the outer solar system, including, of course, KBO, dwarf planet flybys, the circumsolar dust disk, and to view the solar system as an exoplanetary analog of a habitable system. And also, once beyond the obscuring dust disk, the infrared spectrum would, of course, open up to characterize the extragalactic background light, which would give us insight into early galaxy and star formation. And this science, those supporting goals, has then driven the design of what we call the cross-divisional augmented mission concept that we will talk about during this workshop. And now I will pass it over to Elena, our heliophysics working group lead, and she will take you through the amazing science of the heliophysics primary goals. Elena.
Thank you, Pontus. You hear me okay, right?
Yes.
Okay, great. So here is a picture of very intuitive view of what heliosphere is. So the heliosphere plows through the local interstellar medium with the speed 24 kilometers per second. The expanding solar wind meets the apparent flow of the local interstellar medium, and the termination shock is where the outward supersonic solar wind flows and terminates and slows down to create this shock. So the heliosheath beyond the termination shock contains the slowed and shocked solar wind plasma that flows outward and bends around the heliopause, which is the boundary that separates solar wind and interstellar plasma. So this is the hydrodynamic picture. It's very intuitive and it gives you sort of the idea what our heliosphere is. But of course, things are much more complicated. And the formation of the heliosphere is a result of very complicated and poorly understood physics that revolves around not just processes in plasma, but also involves neutral particles that come from interstellar medium, become ionized, and play a major role in boundary formation. Next. It is well known that other stars are surrounded by astrospheres of different shapes, but none of them are like ours. So our heliosphere is the only way we can get detailed insight into the physics of other astrospheres, and also the only way to understand astrospheres around sun-like stars. There is a number of theoretical concepts predicting different pictures how our own heliosphere might look like. You can see them on the right on this slide. And next. As Pontus said, the first and major science goal for the Interstellar Probe mission is to understand our habitable astrosphere and its home in the galaxy. So the first science question is how our heliosphere upheld by physical processes from the sun to the local interstellar medium. The 2 Voyager spacecraft encountered completely new plasma regime in the outer heliosphere, where the pressure is dominated by particles with energies larger than thermal, so-called pickup ions, with energies of a few keVs. Voyagers did not measure pickup ions. That leaves a huge gap in understanding how these particles evolve in the heliosphere and dominate the force balance at the heliosphere edge. Measurements on Interstellar Probe of particle distribution across energy ranges and fields will enable to determine energy partitioning and pressure at the heliosphere boundaries. Now, the termination shock is the largest shock in the heliosphere and was expected to be the strongest, but observed changes in plasma fields and energetic particles at the shock transition by Voyager 2 were completely unexpected. It turned out that the termination shock hits solar wind plasma very little, and most of the solar wind energy, kinetic energy, is transferred to pickup ions or other energetic particles in the heliosheath. Revisiting the termination shock with in situ measurements of ions, electrons, and fields and waves with interstellar probe instruments is crucial to discover energy balance and acceleration processes and turbulence in ions and electrons behavior. Now, the uniqueness of the interstellar probe is in dedicated in situ measurements, but with a balanced complement of remote ENA and Lyman alpha imaging to make use of vantage point far away from the sun. In addition to seeing the changing ENA emission patterns in the sky as interstellar probe goes out, an external vantage point would provide a very unique way of getting more definitive answer about the global shape of our heliosphere, which is very important constraint on global nature and physical processes that acting to create this. In particular, if one could achieve ENA images at around 50 keV range, the large structure would become visible due to longer lifetime of ions convecting through the heliosheath. So on the right side of the slide, you can see how the heliosphere might look like in our ENA images from external vantage point. Next. So the ENA imaging of global interaction on IBEX and Cassini missions discovered bright features in the sky in different energy ranges, so-called IBEX ribbon and Cassini ENA belt. We still do not fully understand processes that create these global features, and going directly through the structures with interstellar probe and measure in situ particle distributions at the source where ENAs are created will help us to understand mechanisms behind these global features, ribbon and belt. Now, when Voyagers discovered anomalous cosmic rays, we expected that termination shock would be an efficient accelerator that produced them. But surprisingly, what we saw that termination shock did accelerate particles, but not to the high energies that has been observed later as Voyagers traversed into the heliosheath. Anomalous cosmic rays intensities continue to roll up as Voyagers move deeper. And so with measurements of particle distributions and fields on interstellar probe in the heliosheath, we will be able to distinguish between several current hypotheses how anomalous cosmic rays are accelerated at the near the heliosphere boundary, where this takes place in the flanks of the termination shock or by turbulence or reconnection processes or something else. So another mystery is from Voyagers that the heliopause is not the surface, but rather a complex region with interactions between heliospheric energetic particles and particles coming from interstellar space. So the open question is, what is the structure and nature of the heliopause? Are there any instabilities playing a role, and what kind of instabilities, and how heliospheric particles escape outside? And another puzzle, we expected that that after crossing heliopause, we would observe a direction of the magnetic field, the interstellar magnetic field, different from the direction of the field inside the heliosphere. However, the direction of the interstellar magnetic field outside the heliosphere appeared to be the same. And this effect of magnetic driving still remains one of the mysteries. Next. Now, this second science question for the interstellar probe focuses on understanding how both variabilities of the sun and interstellar medium affects the heliosphere. We know that the global interaction is highly dynamic. The heliosphere breathes in response to solar wind dynamic pressure changes with solar cycle. And you see the maps during the solar cycle from IBEX High, and as well as ENA maps from Cassini Inca. They show how the global interaction changes, the ENA changes brightness and structures during the solar cycle. And in situ measurements with interstellar probe, together with ENA images, will will help us to establish connections between solar activity and solar transients and structures, global structure of the solar wind, and its imprints at the heliosphere boundaries and ENAs. Now, flows in the heliosheath are also highly dynamic with lots of variations, and Voyager 1 and Voyager 2 actually observed very different flow patterns along the trajectories through the heliosheaths that we still do not understand. And you see simulations here on the right that show very dynamic heliosheath with waves propagating and reflecting between termination shock and heliopause in response to pressure pulses in the solar wind. Also, Voyagers discovered shock waves in the very local interstellar medium with and the nature of those shocks are very different than shocks we observe typically in the heliosphere. However, we still do not fully understand what drives those shocks and how far they can propagate into the very local interstellar medium. So in other words, how far the sun's influence extends beyond the heliosphere. Next. So once we are out to the very local interstellar medium, where we could directly determine properties of the local interstellar cloud for the very first time, we would be given the best information so far to understand how the very local interstellar medium affects the heliosphere. And this would be important for being able to extrapolate how heliosphere responded into different environments through its path in the galaxy. And simulations suggest, as you see here on the left, that different environments, such as, for example, dense neutral clouds or fully ionized plasma around the sun, around in the interstellar medium, would change dramatically the heliosphere structure and size. And so the past interstellar medium we have traveled through so far has not been staying quiet. And there have been dramatic changes in densities and charge fractions, but also supernova explosions that compressed heliosphere even as far down as to orbits of inner planets. And recent findings of ferrum-60 deposits in ocean sediments shows that supernova went off about 3 million years ago, very close to the sun. And its blast dramatically compressed the heliosphere, which possibly exposed Earth to the full force of heavy atoms of galactic cosmic rays that are known to affect atmospheric chemistry. Next. And now we are to the third science question, which is focused on understanding the current very low interstellar medium properties. This is the science that we access once we reach beyond the heliopause and into the unknown very local interstellar medium. Interstellar Probe will enable new discoveries in the science of galactic cosmic rays. Galactic cosmic rays in the energy range between 1 MeV and 1 GeV are deflected by the heliosphere, and thus more than 75% of galactic cosmic rays never reach the inner solar system, where they outside could affect otherwise could affect the chemical evolution of astrospheres. So it's important for general habitability to understand how the astrospheres shield planetary system from galactic cosmic rays fluxes. Well into the pristine interstellar medium, the vantage point of Interstellar Probe allows to measure spectra of galactic cosmic rays that are unperturbed by the heliosphere and provide further insight into the source and interaction with the galaxy. Now, the interstellar dust, which are galactic messengers, we're just beginning to explore the effects of interstellar dust and synergies with the heliosphere science. And you see simulations here on the left, on the right, of interstellar dust propagation inside the heliosphere. And dust and plasma go hand in hand because of the coupling of dust with magnetic fields and charging by flying through different plasma regions. And properties of dust in the heliosphere are affected by different processes at the boundary, such as filtering, deflection, and also processes near the sun. And the open questions for interstellar dust is, for example, how different are properties of dust inside and outside the heliosphere, and what does it tell us about the processes at the heliosphere boundary? And also knowing dust composition and size distribution beyond the heliopause in the interstellar medium would help us to understand chemical evolution of the galaxy. And next slide. The local interstellar medium is completely new area for exploration and discovery, and we know very little about it. We only have sort of a global view, global sort of morphology of the interstellar medium at scales of light years from line of sight spectra toward near stars. And it turns out that the sun, right now, the sun is in contact with 4 interstellar clouds with different properties, and actually is leaving the local interstellar cloud with a relatively short galactic timescale, about 1,000 years. But the ground truth of properties of the very local interstellar medium is missing. We only have sort of sparse understanding inferred from measurements inside the heliosphere of interstellar helium and picopions, ENAs, or backscatter Lyman alpha emission. With Interstellar Probe, beyond the heliopause, we would be able to sample directly the interstellar magnetic field, the particles across large energy range, interstellar neutrals and dust, and measure composition and charge fraction, and responsible ionization processes, and also the force balance in the very local interstellar medium. And this would provide the first insight to the heliosphere's location within the local interstellar cloud, and also will provide the decisive information on the global heliospheric interaction. And now I would like to turn it back to Pontus, who will talk about the cross-divisional science opportunities on Interstellar Probe.
Thank you, Elena. All right. Unfortunately, I won't spend much time here. Others will spend more time on this later. But when it comes to dwarf planets and KBOs, there are over 130 dwarf planets out there, and there are probably more than 4,000 KBOs, and that's a number that just seems increasing, and the Kuiper belt seems to be also expanding the more we look, in fact. So any direction that would be picked by sort of the primary heliophysics goal, there's always one out there for us, as I think Bill McKinnon said during the 2019 workshop. Okay, so Orcus and Quasar that we depicted here, there are only 2 examples and out of a dozen intriguing dwarf planets in this possible path of an interstellar probe. So Kirby Runyon, he will talk about this in more detail, 11:20 on Wednesday. Then the solar system is also surrounded by a dust disk, a circumsolar dust disk, which is sort of a remnant from the formation of the solar system. So it's, of course, extremely important to understand. Other such dust disks, they of different ages, they've been observed around other stars. And very surprisingly, like the one you see here, HL Tauri, they revealed planetary formation that begins much, much earlier than we previously expected. The sun's dust disk is sort of a great example of a mature system, and we have, of course, increasingly detailed knowledge of it, of the formation process of our own solar system. However, we don't know what the sun's dust disk really looks like in large, since we're sitting inside of it. Our observations along the trajectory would then be able to reveal the large-scale structure for the very first time and provide this invaluable ground truth for planetary formation in general. And Jamie Zalai, he will talk about this in a little bit more detail tomorrow already at 12:30. And then once we get beyond this obscuring dust disk, starting actually already at about 10 astronomical units, the spectrum of the infrared extragalactic background light would become detectable, would pop up above the background. And this would provide also insight into early galaxy and star formation some 200 million years after the Big Bang. And Michael Zemkov, he will talk about this in more detail at 11:40 Eastern on Wednesday. Okay, so now to something much different, but very related. And some people balk at this, but it's a very, very necessary exercise that we've gone through in this study. So to capture all of this science and flow it in, importantly, into a pragmatic mission design, we have now finalized the Science Traceability Matrix, the STM. You'll find this full-blown STM on a fold-out And I think very shortly we'll actually put that folder also on the website. So I encourage you to take a look at that. These slides, again, you'll find those on the website so you can follow along. So here you see the SDM of the baseline mission with one example model payload that could be flown. This flows the overarching goal on the left here through 3 science questions that Elena just went through that deal with the current state of physical processes of upholding the heliosphere, its dynamics, and then thirdly, the interstellar medium itself. This in turn flows to a set of objectives and investigations that then dictates the types of measurements that are needed and where, as indicated here with a color code. The middle column here details the measurement requirements and the requirements to results of the spacecraft. And then the last column state the mission requirements. And lastly, the very important closure, where all the science results are sort of pulled together to understand the current state of the heliosphere and having that knowledge to also ultimately extrapolate to the past conditions and also to future conditions. These 2 remaining slides and versions we have distilled down the augmented science traceability metrics of goals 2 and 3, and others will talk about this tomorrow as well. And as you see here in blue, only 2 instruments have been added in this example, but provides really a science return worthy of a planetary/astrophysics mission alone. And lastly here, these are the trades that were made to the primary goal number 1, by adding these 2 instruments that you see here in gray. I've no time to go through this here, but please take a look at this offline. And obviously, many of you have been tightly knit into this long development of this traceability matrix. Okay, so one of my favorite slides. I showed these slides during our second workshop in the Explorers Club in New York, and that's where we sort of fixed the mass allocation. And it still very much applies, I think. Before we launch into tomorrow's discussion on measurements and example payloads, everyone needs to understand that we have intentionally fixed the mass allocation from the beginning. We have done so not because those are all the instruments that we would ever need, but to ensure that we're doing a realistic trade exercise that can benefit a future science and technology definition team that will be faced with pretty much the same challenge. The mass allocation here is, of course, not arbitrary, but it represents the typical flown payload to spacecraft mass ratio, as you can see here. And Interstellar Probe sits in a place pretty similar to Voyager with a slightly more conservative assumption, I think. Here are the 2 example model payloads that could fly. And again, to define exactly what model payload or final payload will fly, that's the job of a future science technology definition team. It is not our job under this study, of course. The baseline example payload, it focuses on heliophysics only. Here the spacecraft would be a sun-pointed spinner that Ralph showed you in the nice movie in the beginning. The mission design is driven here mostly by the need to carry the long wire antennas to measure the plasma waves. And these are, of course, centrifugally deployed. And also, of course, plasma physics measurements, we often require the spacecraft to be spinning to maximize the angular coverage. Our guiding principle in these trades that is sort of alluded to here on in the percentage bar on top here is that in situ measurements, they remain a high priority, but we do want to maintain a sort of a balanced complement of a powerful remote imaging as we go out to a very different vantage point. In the augmented example payload, 2 unique instruments have been added. As I said, it's the visible near infrared and infrared mapper for flybys and astrophysics. And a balanced trade has been made here with the Lyman Alpha instrument to accommodate for for those two within this fixed mass allocation. So being driven by the KBO flybys, this augmented scenario relies on a 3-axis thruster control spacecraft. Much like New Horizons, this enables, of course, the spacecraft to go from spin stabilized, satisfying our plasma physics measurements, to 3-axis during the flyby, and then back to spin stabilized. This, of course, also necessitates that the plasma wave antennas are shorter and rigid. The option to centrifugally deploy 50-meter wire antennas after the flyby has been analyzed, and it does remain a severe sort of level 5 risk to the mission. So that has been noted. We will spend more time tomorrow and on Wednesday when Alice and the team will talk more about these trades in detail. So this has changed a little bit over the study here, actually. So this is the way we think about the launch options and the opportunities. So these opportunities really open up towards the forward hemisphere of the heliosphere, beginning already in 2036. So we've sort of carved out the forward hemisphere, the noseward hemisphere of the heliosphere. And they're followed by a range of opportunities to maximize the outbound speed about every 13 months. And don't worry, I know the speed contour map here looks very complicated, but you'll see this many times in this meeting. We've gone through about 6 different trajectories where each one of them have specific scientific advantages and trades. And you'll hear more about this on Wednesday and on Thursday. And now to the very important preparation for the decadal. Elena, please.
Thank you, Pontus. So we are preparing for the upcoming Heliophysics Decadal survey and coordinating white papers about the importance of our heliosphere science and demand for new measurements. And there are more than 30 white papers currently being prepared, covering all the different science topics that we talked in this presentation. Also, before the Helio 2050 workshop, we had began very successful series of Zoom meetings to talk about white papers, coordinate efforts, and discuss important science questions in the outer heliosphere and interstellar medium science. And we have very exciting upcoming talks this fall, and you see the list here. We're looking forward to these interesting talks, and so please join us. Also, we are in the process of converting white papers we write and different study results into peer-reviewed journals, and also getting ready for preparing the Interstellar Probe book. And next slide, please. So in the upcoming AGU fall meeting, we will have a session, the Interstellar Probe, emission through the heliosphere edge into the local interstellar space. And so please join us for the session. We will have 2 exciting invited talks given by Alice Kokoris to talk about instruments and payload, and also from Pavel Svazina from Princeton, who will talk about interstellar neutral atom observations on the Interstellar Probe. So please join us. It will be both virtual and in person as of today. Thank you, Pontus.
And with that, to also battle the Zoom fatigue, we want to make sure that we leave some room for questions. And as always, let's begin. So I see we already have a few questions here. The first one is from Marshall Eubanks. Will there be any attempt to target the apparently close boundary between the local interstellar medium cloud and the G cloud, where the Alpha Centauri system resides? Elena, would you like to take that one, or do you want me to take it?
I can certainly comment on this one. Thank you for this question. That's very interesting question. So according to recent studies, and I'm referring to Linsky et al. 2019, the heliosphere may already be in contact with cloud with 4 different clouds, including the G cloud and others. So this new study actually emphasized that about 45% of the sort of heliospheric coverage is by local interstellar clouds. So other areas are covered by other clouds. So we may be already in contact with G cloud, but we can't say for sure without in situ measurements, making in situ measurements in the interstellar medium. So those measurements will provide reliable basis for studying properties of local interstellar cloud and local interstellar medium, and hopefully give us a better insight of where we are actually.
Thank you, Elena. The next question we have here is, let me just mark this off, is from Tony Freeman again. And I can take this one, would the expected number of known KBOs increase significantly later this decade as the reach of ground-based telescopes extend, and with systematic surveys for faint moving objects like LSST and the NEO-SM? The short answer is, I believe you betcha it will. I know there are sort of ongoing studies, and I'm following by interest also the developments on the New Horizons side, and there's a lot happening, and the more I hear, the more I see that the Kuiper belt seems to expand more and more as we're looking at it. And I think actually we can take this question up also in the open discussions, and I certainly know that both Kirby Runyon and Bill McKinnon is online. So in the open discussion later today, this might be a question that they could provide more answers to.
I can take the next one, Pontus.
You can take the next one, please.
Yes, Andre Gali is asking, when is the deadline to submit white papers to the decadal survey? I think as of today, there is no deadline yet, but we expect it to be sometime in spring 2022. Pontus, do you have any more updated information?
I think the latest we said, Elena, in your group was that we wanted to aim to have white papers in a good draft form before fall AGU, and I think that's a deadline we ought to keep, right? To get them.
Yes, this is the deadline for sort of the community who has been involved in white paper preparation. But I mean, the deadline from National Academy, I think, is not set yet, right?
No, it's not.
Yeah.
We know the previous schedule has been shifted and delayed by about, I think, 3 or 4 months. But we can certainly provide more detailed information later.
And there is a number of white papers already written and ready to post on the website. This is what we will do after the workshop.
Yep. Okay. We have another one here from Nibin again. Hi, Pontus and Elena. Could you kindly explain the difference between plasma system and plasma wave system? Plasma system and plasma wave system used in a Voyager 1 spacecraft, and news on any breakthrough signals with respect to the Interstellar Probe mission. I can take the first half of this one, and I think what Nibin is alluding to here is the instrumentation. So on Voyager, there were 2 rigid sort of tape measure antennas, and they were 10 meters each. On Interstellar Probe, in the concept that we have now, there will be 50-meter wire antennas that would be centrifugally deployed shortly after launch, actually. And the good thing about this is you really want to go thin on these wire antennas and long, because what you can get to then is of course the plasma density, the electron density out there, and even the temperature, was extremely important for the interstellar medium. And the problem or the challenge is that if you look at plasma instrumentation, just detecting the particles themselves, this is sometimes very challenging because you're also fighting the spacecraft potential. However, out in the interstellar medium beyond the heliopause, we do expect that the spacecraft will only charge up to a few volts, 5 volts or so. So that will sort of facilitate also measurements of the low plasma density. And Elena, maybe you want to take the last half of this question on the news of breakthrough signals and refer to Stella's talk.
Well, I just actually, I wanted to sort of keep intrigue and wait for a stellar talk.
Yes, exactly.
And hear from the author of this analysis. That would be very exciting.
Yeah, so this is a pitch for Stella Åker's talk, and she will provide a beautiful, detailed presentation on these new breakthrough discoveries. Okay. Oh, we have a good comment here, I think, from Eric on the delay here. National Academy has asked to delay the Heliophysics Decadal study because they have too much going on. Yes, and don't have enough people. No date has been agreed between the academy and the headquarters yet. Okay, thank you for that answer and comment, Eric. Okay. All right. Do we have any other questions? We'll wait a couple of more seconds, and if not, I suggest that we give ourselves a break. And Michael, the next break will be at 12:30 originally scheduled, right?
Yes. Our next break is scheduled for. Let me make sure I'm actually looking at Monday again. Okay. We were going to run this session until 12:30. We can certainly take a couple more questions if folks have more they'd like to learn from Elena and Pontus. As they said, it's going to be a lot more detail on many of these science subjects later on in the week. Nibbin says, congratulations on your feat of achieving the fastest ever spacecraft in space, the Parker Solar Probe. Yes, thank you. APL is quite proud of that, and there are several people in this study who are working on Parker, including Jim Kinnison, who you will hear from later, and Ralph, who's got an instrument. He's a co-investigator on one of the science instruments. The connection between Parker and an interstellar probe is very strong. Ralph talked about the 3 studies about exploring our solar system, about exploring our heliosphere, and this is the one of the 3 that has yet to be done. So building on Parker to set the path for interstellar probe has very much been a part of the discussion from the beginning. But yes, I'm happy to give another 10-15 minutes back to ourselves and to our guests today. And with that, I want to say thank you, Pontus and Elena. Excellent presentation. Thank you all for your questions so far. It's been great to have the dialogue going that we've got today. And we're going to go ahead and put all of ourselves on mute, and we will be back at, let me just confirm the time one more time so that I do not steer all of us astray. We will be back at, oh dear, too many windows open here.
It will be back at 1 o'clock, Michael.
At 1 o'clock p.m. Eastern time. Thank you, Andrea. Keeping everybody on track. I appreciate it very much. We'll be back at 1 o'clock. We look forward to seeing you at 1 o'clock p.m. Eastern time, where Jim Kinnison is going to kick off the afternoon with a discussion about the mission concept as a whole. And thanks all. We'll see you again soon.